Okay, well, it's our pleasure to be introducing Chris Fry, who works on physics of jets in high energy physics, so particle physics, and has now recently been in the field of machine learning. He's a graduate student here who will soon be finishing up his degree. Now, I just wanted to tell you something I told Chris. Chris is going to show us very sophisticated ways of analyzing data that comes from particle experiments. When I started graduate school, down the hall from me was a big room that had many huge scanning machines, and there were about 5 people employed full-time who would look by eye at the film as it passed over a light table. And they were given instructions on which types of events they should flag. And so when they did that, that would next go on to a graduate student who would, filter it further, and then to an assistant professor or a postdoc, and then finally to the full team. So from his talk, you'll see how far we've come in the meantime and what an important role machine learning has to play. I also want to apologize that we did not get a good film last week. So Raphael has kindly agreed to give another talk that we can film, and he has also made his slides available, which I will post for you. Today we had Sean in the control room, and we expect to have a great video. Yeah, thanks. So Chris.
Thanks for the introduction. I just noticed that my slides got cut off a little bit. Okay, so today I'm going to tell you about some work that I'm finishing up with a couple other people, fellow graduate student Anders Andreasen, previous graduate student Ilya Fage, and my advisor Matt Schwartz. We've been working on a general approach to unsupervised jet physics, so I'll tell you about that. And I'll start with an introduction to jet physics and a little tiny introduction to the type of machine learning that we're using for jet physics. Okay, so first, what is a jet? Well, in short, a jet is a collimated set of momenta, and these are produced all the time at particle colliders. On very short time scales, at particle colliders, there's a very high energy collision. For example, maybe a positron and an electron will collide and turn into a quark and an antiquark. And then on much longer time scales, the quark and antiquark will emit many soft gluons, and those gluons might undergo collinear splittings, and there will be many particles produced. Eventually, all these quarks and gluons will hadronize and become stable color-neutral particles that hit our detector, and this collimated spray of momenta that hits our detector is what we call a jet. So let me tell you a little bit about why jets are so important. So first, they're just an inherently interesting emergent phenomenon of QCD, and learning about them helps us learn about quantum field theory. They're also useful in the search for new physics, especially because most of the very clean ways to search for new physics, like with hard leptons or photons or things like that, have already been explored, and now we need to look at the much messier objects of jets. And they're also crucial for precision standard model measurements, and let me give you an example of why. So here's a pie chart that tells you about the Higgs decay modes. So a Higgs decays, 61% of the time to quarks, 9% of the time to gluons, 21% of the time to Ws, 6% to taus, and 3% to Zs. But actually, a lot of these decay channels actually show up in the machine as jets. First of all, that's because quarks and gluons evolve into jets. So the blue and the green, that's just jets. And actually, the WW pair that the Higgs boson can decay to, well, 4% of the time that will go to only leptons and neutrinos, but 96% of the time the decays of the Ws will involve jets. And there's a similar story for the tauons and the Z bosons. So actually, 98% of Higgs decays involve jets. And as you can see, all these jets came from different origins, and it's vital to be able to distinguish jets of different types, and that's part of what we can use our work for, as you'll see soon. Okay, so a couple slides ago, I drew a couple momenta and circled them and told you that's what a jet was. But there are actually precise ways to define jets in particle colliders. Usually jets are defined by what's called a jet clustering algorithm. The one I'll tell you about today is called Cambridge-Aachen, and it's just based on angles between momenta. Specifically, the Cambridge-Aachen jet algorithm involves sequentially clustering pairs of momenta and always clustering the pair with the smallest opening angle. And you just keep clustering the pair with the smallest opening angle until you stop when the smallest opening angle exceeds some fixed parameter called the jet radius. So in this example, maybe 10 particles, 10 momenta hit the detector, and this shows you how you would cluster them up according to the Cambridge-Aachen algorithm to find two jets. So maybe P4 and P5 had the smallest opening angle, so we'd cluster those first. Then maybe P8 and P9 have the next smallest, so cluster those next. And you just keep going until the smallest opening angle exceeds some parameter called the jet radius, which is usually some order 1 number. And in this example, the first jet has 6 momenta, and the second jet has the remaining 4 momenta. And one important thing that you can see already is that jets automatically come with tree structure, and we will use this in our machine learning model later. Okay, so now let me tell you about what's been going on briefly in machine learning and jet physics. So this is a field which has been exploding in the past 2 years roughly, I guess now. We just had a workshop at Berkeley in December. And many of the projects that have been going on in this subfield have to do with classification or regression. For classification, one example of a popular thing to study is discriminating between jets that were initiated by gluons versus those that were initiated by quarks. That's a hard problem. An example of what's been done in regression is pile-up subtraction, being able to eliminate those momenta from jets that actually came from other collisions, not the collision that you're interested in. And as we were starting our project, we tried to ask the question if we could learn some physics from our machine learning algorithm. For classification, for example, you can teach the machine to be an excellent classifier, but you really don't know what it's learning about why quarks and gluons are different that allows you to classify them. So we're hoping to be able to look inside and learn something from the model. So our idea is to let the neural network learn about jets and then look inside to see what it's doing. And especially the second point is notoriously difficult because machine learning neural networks are like black boxes almost. Okay, so let me tell you first how we did not do it. So I just presented some conflicting goals for the neural network. We want it to be flexible enough to fit any data, but we also want it to be transparent enough to probe what it learned. One thing you might imagine that we would do is have some generative model where you feed it a seed, it propagates through some neural network, and out comes a jet. Out comes the momenta of a jet. This is not what we want to do because we have no idea what's going on in the intermediate layers. So our strategy is to use a network architecture that's inspired by the QCD tree structure. And that way, as you'll see, we'll be able to interpret some of the output from intermediate layers. But we'll also do it in such a way that's general enough to fit any non-QCD shower structure. Okay, the architecture that we chose to use is called a recurrent neural network. RNNs are natural for modeling sequential evolution, for example, as in language. One nice thing about them is they allow an indeterminate number of time steps. So jets don't have a fixed number of momenta. They could have 10 particles, they could have 20 particles, so this is a nice feature of RNNs. And let me tell you very briefly how RNNs work for sentences. So HT is like the state of the sentence, some hidden representation that the machine learning model has of the sentence at time step t, or at word t. So let's say you're texting and your phone is trying to predict the next word that you're going to type. It has some hidden representation of what you've typed so far, HT. It uses that hidden representation to predict the next word, t plus 1. And it maybe presents you with 3 options of words you might want to type next. When you actually choose your next word, that updates the hidden representation to HT+1, and then it makes another prediction. It's common to wrap this picture up into this abbreviated picture because the parameters that take each word and each hidden representation from the previous time step to the next time step are all the same. And so this is how we draw RNNs. And we're going to use an RNN to model jet evolution. And there's a rough correspondence that the sentence is like the jet, and the next word that we're trying to predict is like the next splitting in the tree. Any questions so far? Yeah.
Do you have access to several steps back in the chain, the information, or?
So HT has some memory of what's happened, but in predicting word T+1, only HT is used. But we don't really know what's inside HT. The model learns, the machine learning algorithm learns how to model that itself. Okay, so now let me tell you about our model. Okay, so what our model does is it computes the probability of a jet. So I'll be writing P of jet a lot, where jet is just the set of n momenta, where the jet consists of these n momenta. And the probability is inferred from the training data, and I'll show you how that works. Okay, so let me say a little bit about probabilistic models in general. So our model P theta of jet has many parameters, theta, and we also have a bunch of data to determine what the best parameters theta will be. I'll tell you more about our training data later. And so we want to choose these parameters theta such that they maximize the log likelihood of the data given our model. So that's what this says here. This is how we choose theta. And in practice, we approximate this maximum using stochastic gradient descent, where we take steps. We go from theta n to theta n plus 1 according to this gradient ascent equation, basically where it's stochastic because you don't compute the gradient using all the data. You split the data up into mini batches. You take a small step of size determined by the learning rate and the gradient of the log probability computed on this batch, and you keep doing that until you start to converge to the optimal model. Okay, so now I'll spend the next few slides being more and more precise about our model. Okay, so as I said before, to minimize complexity and maximize the interpretability of our model, we want to represent this probability, P of jet, as a sequence. We do not want the sequence to correspond to the unobservable quantum mechanical parton shower because that's not physical. We can't see that in data. We use quantum field theory to describe that, but when particles hit our detectors, we don't know what quantum mechanical process they went through before they got there. Instead, we want to use the clustering tree that I told you about earlier. Okay, in particular, it's called the Cambridge-Aachen clustering algorithm. Okay, and let me go into a little bit of detail about that. This isn't so important, but I just want to convince you that in setting up our model in the following way, we haven't made any approximations or assumptions. Okay, so I need to define some variables that are inside this tree. So each line I've drawn is like a different time step in the tree. So these are the particles that hit the detector, P1 through Pn. As you cluster them, you build this tree. But now we're going to start thinking about the tree going this way. So it's kind of like you start with a particle, it splits, then that one splits, then that one splits until you have the whole jet. And so each momentum in this tree is labeled by KIT, where the subscript I is the number of the particle in that time step, and the superscript T is which time step you're at. And of course, the last time step is the full jet. Okay, so now let me show you how we wrote P of jet using all these variables. Okay, so first we factorize P of jet as a product over time steps, so the probability of the full jet starts as the probability that you get from the first momentum in the tree to the 2 momenta at the second time step. And then you keep going until the tree ends. So let me call each of these factors P of t, where t is 1, then 2, then 3, all the way up to n. And furthermore, we factorized each P of t in the following way. Okay, so let me tell you why we factorized it in the following way. So look at this factor, for example. It takes n minus 1 momenta into n momenta. But really, only one momentum split into 2 momenta, and the rest of them all stayed the same. So we want to take advantage of that and simplify P of t. So that's what I've said here. Each declustering involves a single 1 to 2 splitting that we're going to call parent splits to daughters. And that parent splitting into daughters depends indirectly on the rest of the jet at that time step. So what I'm writing here is P of t is factorized into 3 factors. First, there's the probability that the shower does not end at that time step. Second, there's the probability that whichever parent splits is the one that splits. And then there's the probability that whichever daughters were the result of that splitting were chosen. And all of these factors depend on ht, which is the representation of the rest of the jet at time step t. Okay, so there's no loss of generality here. I haven't assumed anything. I've just rewritten this giant P of jet into a bunch of factors. And let me sort of summarize that on this slide. So, in summary, our model computes the probability of a jet. It does it as a product over time steps defined by a clustering tree. So P of jet equals P of t1, P of t2, all the way up to P of tn. And each time step is factored into 3 parts. There's the probability that the shower doesn't end. There's the probability that a certain parent is the next splitter. And there's the probability over the daughter momenta that that parent can split into. Okay, so this is the general structure of our model. Okay, and next I'm going to start telling you about how we've implemented this using a recurrent neural network. Okay, so those 3 factors are now at the top of the screen, and there are neural networks that output each of those probability distributions. So there's a neural network dedicated to ending the tree, a neural network dedicated to choosing the next parent, and a feed-forward neural network dedicated to the splitting into daughters. And there's also an RNN that keeps updating itself as it gets new data about the jet. So if we're trying to compute the probability of this jet, this picture tells you about the probability associated with a certain time step. The daughters from the previous time step are fed in to update the state of the jet, ht. And then the parent that was chosen is fed into the splitting that decides its daughters. So this is a little more detail about our model. Any questions? Okay, and the next few slides I'll go into the more the structural detail of each of these components, each of these 4 components. Yeah.
Recap, the first top 3 are neural networks. These are the feed-forward networks.
Yes.
One in the middle is the bottom one is the recurrent neural network.
That's right. Yeah, and I'll show you what they look like.
The outputs, the top 3 are put into the bottom one.
So if we have a jet and we want to compute its probability, then the outputs are just the probability of whatever happened should have happened. And then whatever actually did happen is fed back in to update the RNN and predict what should happen in the next time step. If this were being used to generate a jet by itself, then yes, we would draw from the probability distributions at the top and then feed the new draws into the bottom to propagate into the next state or next time step.
I guess to follow up on that, let me see if I understand. So you're feeding the daughters from step t minus 1 into the RNN.
Mm-hmm.
So that's coming from the net that you have on the right?
Yes, if we were generating a jet, then we would draw from that net on the right and feed those back in.
Okay, but if you're not generating a jet, how do you use the information from the previous time step to feed the RNN?
So if we're not generating, then let's say we just have some jet that we either got from a simulator or from data and we want to compute its probability, then we already know all the parents and all the daughters. We're just trying to compute the probability of everything that happened.
So you're putting in the real thing?
Yes, exactly.
I see, thank you.
Any other questions?
So the data you get from the detector tells you what happens in each branch, probably just at the end, right?
So yeah, the data that you get from the detector tells you these momenta, but then the clustering algorithm tells you how to make a tree out of them. It tells you combine two momenta that have the smallest opening angle, and then combine the next two that have the smallest opening angle, and then combine the next two and the next two until you're done. So given the momenta that you see in the detector, you can always make this tree. And so you can always feed that tree into our model.
Is there an inverse problem, or is it always uniquely defined?
It's always uniquely defined because there's always a pair of momenta that have the smallest opening angle. Okay. Okay, so that picture that you were just looking at is now over here, and I'm going to tell you about each of those four components. So first, let me tell you about the RNN. The RNN is HT. It's some hidden representation of the jet of dimension 100. That's what we chose. It seems to work. To update HT with the information from the previous time step, it takes as input HT minus 1 and the daughters from time step t minus 1. And those are just fed forward. The lines in this picture indicate matrix multiplication by weights that our model is learning through gradient descent. And the nodes represent a nonlinear function like a ReLU or a tanh or a sigmoid. So just to be clear, only the latest two daughters and HT minus 1 feed forward to time step t. And so we rely on this recurrent representation of the jet to maintain knowledge of the global jet structure in predicting everything that should happen next. Okay, so HT is about to feed into P end, P parent, and P splitting, and I'll show you that next. Okay, so let's talk about ending the tree. So I just showed you where HT came from. Then that feeds forward into a hidden layer. Again, we chose dimension 100, it seems to work. And then that feeds forward into an output layer. The output layer is a sigmoid that predicts the probability that the shower should end at that time step. I guess this comment was for another talk where they weren't so familiar with neural networks, so I just told them to think of this as a black box. But if you have any questions about this neural network, please ask. Okay, the other two components are similar. HT feeds forward into a hidden layer of dimension 100 again. Then that feeds forward into an output layer. This time the output layer has many nodes because there are many possible parents many possible candidates for the next parent. And the way that we get a probability distribution out of those output nodes is using a softmax, which is like the many node version of a sigmoid. Basically, you just exponentiate and normalize to turn the real numbers in the output layer into a probability distribution. Okay, and the nodes in the output layer are in one-to-one correspondence with the particles in the intermediate state in an energy order. So if we're sampling from this output probability distribution and our sample chooses the first node, that means that the highest energy particle in this intermediate state should be the next one to split. Okay, and a similar story for the splitting model. So again, HT feeds forward into a hidden layer of dimension 100. There's another input to this layer, which is the parent that was just chosen in the previous step. And then the output layer has many nodes that determine what splitting should occur next. We've chosen to discretize the splitting in the output layer. We have discretized the continuous splitting into 10 to the 4 cells. I'll tell you how that works on the next slide. But basically, There's a softmax over these nodes as well. Whichever one is chosen determines how the daughters should come out of the splitting.
How did you choose the number of nodes in the inventory?
So we didn't fine-tune at all. We tried 10, we tried 100, we tried 1,000. 10 didn't work as well as 100, and 100 worked basically as well as 1,000. So it seems like 100 has enough capacity to learn what it needs to from these jets.
So this question of capacity, just that you're getting results that you're satisfied with, is that?
Yeah, and I'll show you lots of results.
I mean, how do you know that you wouldn't get something different if you tried 105 or 94? You know, is there a systematic process that could be used in this, or is it really at this point kind of a coarse-grained trial and error?
As far as I understand, it's a pretty coarse-grained trial and error. And we definitely expect that 94 and 105 should behave extremely similarly to 100. But that if you multiply by a factor of 5, for example, you can get you have a lot more capacity and you could model things a lot better if you're leaving things out using 100.
But it slows things down.
Oh yeah.
And it might not be better, right? I mean,
If
harder to train model.
True. Yeah, like once you take practical considerations into account, if you can't train it to convergence, then it might not be better. That's right. Okay, so here's how we parameterize the splitting. This isn't so important, but I'll go through it. So there's some parent momentum that splits into two daughter momenta. These are four vectors, four momenta. So one four momenta splitting into two four momenta. There's 4 free parameters in choosing the daughters because it's conservation of momentum. We choose z, theta, phi, and delta to parameterize those 4 degrees of freedom, where z is the energy fraction that goes to the softer daughter, theta is the angle between the parent and the softer daughter, delta is the angle between the parent and the harder daughter, and then phi just tells you how this thing is rotated azimuthally. And so we discretized each of z, theta, phi, and delta into 10 cells, resulting in a grid with 10 to the 4 cells. Okay, and so z, theta, phi, and delta are not all sitting in the 0-1 unit interval, so we shifted and scaled them so that they were. This isn't so important. We also took logs because many of these distributions are naturally very peaked towards smaller, large values. So this is called feature scaling. So that's what we did. Okay, so next let me tell you about training, unless there are any questions about the model. Okay. So we took a set of training data from a simulator called Pythia as a proof of concept, but everything that we did using the simulated data could be repeated on real LHC data. In particular, we used 500,000 jets generated in E plus E minus to QQ bar collisions at a center of mass energy of 1 TeV. That means that each hemisphere jet had about 500 GeV in energy and had a jet radius of about pi over 2. And then we turned these jets into trees using the Cambridge-Aachen jet algorithm. And just to be complete, we actually cut off the trees when the opening angles got to about 0.1 and when emissions fell below 1 GeV, just to pretend like we're using some detector resolution cutoffs. Yeah.
What is a hemisphere jet?
So a jet is a collimated spray of particles, and you get to choose the jet radius as you're walking through your jet clustering algorithm and deciding when to end clustering. So a hemisphere jet means you keep clustering until you have 2 jets, and each of them is roughly taking up pi over 2, so a hemisphere.
I see. So you're just getting the whole thing.
Yeah, yeah. Okay, and we used a program called Theano in writing our model. Okay, I already showed you the slide, but this sums up everything we did to train our model. we just split our data set of 500,000 jets into mini batches, and we used stochastic gradient descent to optimize the model. And we used several different batch sizes and learning rates that, if you're interested in, I can tell you about. And training takes a couple of days on 16 cores. Okay, so now let me show you a few plots that sort of validate that our model has learned properly. These plots will be in close correspondence to the different components of the model that I showed you earlier. So the plots on this slide correspond to ending the tree. Both the left and the right plot are plotting the probabilities that the tree should end. On the left side, it's a function of the intermediate state length, and on the right side, it's a function of the maximum angle between a particle in the intermediate state and the jet axis. The two distributions that I'm comparing, one of them is from the simulated jets from Pythia, and the other one is our network being evaluated on those jets, and this is the probabilities that it output, and you can see that they are in good agreement. Yeah. Okay. No, we use CPUs. Couple days. We didn't have one. We didn't have access to one at the time, and this worked fine. Okay, so this is a first validation of the N-shower network. I'll show you many more results later, but we'll start with these.
I should say, this isn't obviously parallelizable in the same way that a convolutional network would be. It may not so efficiently run on the GPU. I think you can do it, but the speed improvement won't be tremendous.
Yeah, with a recurrent neural network, you cannot parallelize over time steps because the results of time step t feeds into time step t plus 1. So there is some things that you cannot parallelize. Okay, so next let's look at a couple plots validating the choose next parent portion of our model. And both of these show the probability that a candidate should split next. On the left, it's a function of that candidate's index in an energy sorted state. On the right side, it's a function of that candidate's angle to the jet axis. And again, we're comparing Pythia to our network evaluated on Pythia and outputting the probabilities that it's predicting. And you can see that these agree pretty well as well. On this last slide, we're checking the splitting model, part of our network. So I told you that we parameterize splittings in terms of 4 parameters, z, theta, phi, and delta. In the top row, we're checking z and theta at time step 0. In the bottom row, we're checking z and theta at time step 10. So you can see that the distributions evolve in time as you go from time step 0 to time step 10. For example, let's look at the angle. At early time steps, splittings are wide angle. At late time steps, splittings are narrow angle. That's because of the clustering algorithm that we're training on. And you can see that our model agrees pretty well with the simulated jets that it was taught to agree with. Okay, and by the way, this sort of flat part in the z distribution shows that our model is learning something closely related to the QCD splitting function. So there's a splitting function that tells you the energy fraction of emitted gluons from the hard quark, that it should be distributed as like 1 over z. And since this is a roughly log z, that's roughly flat. That's just showing that our model is learning some physics, as of course it must. Okay, and the result of all these shows that the RNN really is storing global structure. At every time step, all it gets is this black box hidden information from the previous time step as well as the latest 2 daughters, and somehow it knows the energies of all the particles in the states, their angles with respect to the jet axis, and it's really understanding and storing the global jet structure. Okay, so next I'll tell you about some applications and results that we've been looking into. Okay, so now that our model is trained, given any example jet, we can compute its probability just by feeding it through our model. So here's an example jet from simulated in Pythia, and at each node, I've plotted the probability that our model assigned to what happened at that time step. And I've plotted the log base 10 probability. So here, for example, our model said that, there are three things that, well, let's look at this one. So there are three choices that had to be made at that time step. First, the tree did not end at that time step. Second, this particle was chosen to be the next parent and not this particle. And then third, these two daughters were chosen as the next two particles in the tree. And our model computed that all those things put together had a probability of 10 to the minus 3 of happening. So this is a way of visualizing the probability that our model assigns to a jet. And by the way, the color scale tells you about the energy of each leg. Okay, so maybe you're wondering now, what can we do with this probability? This jet, for example, had a total probability of 10 to the minus 39. So what is that good for? Well, I'll tell you about three things. One thing we can do is use it to discriminate different types of jets. We can also generate jets by drawing from the probability distribution. And we can use it to reweight simulated jets so that they agree with data distributions. And let me go through each of these now. Okay, so first let's talk about discrimination. So, so to do discrimination, we used two data sets. One was jets initiated from high-energy quarks. The other was jets initiated from high-energy Zs that decayed into QQ bar, which then evolved into jets. And there's a lemma that says that the most powerful Z versus quark jet discriminant would be the likelihood ratio. And since our model computes the probability of the jet given the Z model or the probability of the jet given the quark model, we can plot this. And of course, this lemma is only relevant if our model is good. So just make sure I say that. Yeah, I did E plus E minus to IZs.
And you're not picking a regime where they're
So it's a 1 TeV E plus E minus collider, and I cut on the mass of the hemisphere jet to be within 1 GeV of the Z mass, just so there would, just so that the model is learning things besides mass to discriminate.
So yes, they are boosted.
They're boosted. I'll show you some pictures too. Okay, so here's a plot of the likelihood ratio that I said we should cut on if we want an optimal discriminant. You can see that it does separate the quark jets and the Z jets pretty well. And here's a plot of the ROC curve that tells you how many Z jets you can accept and while rejecting a certain amount of quark jets. Now, this is mostly just a proof of concept that our model, that these probabilities are meaningful and useful. Quark versus Z discrimination is not the most interesting thing to study. And tau 2-1 plus multiplicity is not the most interesting discriminant to compare to, but I just wanted to put these up to show that it works. So tau 2-1 is an observable that tells you something about how two-prongy a jet looks. So a Z decays to QQ bar, and so the resulting jet has two hard prongs in it, whereas a quark that evolves into a jet has one hard prong in it. So this is some analytic observable that's well understood that can discriminate between Zs and quarks pretty well. And also the multiplicities, basically how many particles are in a quark jet or a Z jet, is also a pretty good discriminant. But of course, since our model can take advantage of much more information than those two simple observables, it does a lot better. We're interested in testing it on more important regimes in the future, but this is what we've done for now.
Can you also look at the correlation between the different observables, the different parameters that you're considering?
Like two different observables? like, I will show some plots of correlations. Maybe I'll come back to your question then in a couple minutes. Okay, and one thing that I'm really excited about is being able to visualize the discrimination power. So earlier in the talk, I talked about how machine learning has been being used to classify jets, but you really don't know what the model is learning to classify those jets. In our case, since we've split our model into a product over time steps in a clustering tree, we can literally plot the likelihood ratio at each time step of a given example jet as we're trying to decide whether this is more likely to be a quark jet or a Z jet. And so we can see which parts of the tree are giving the discrimination power and possibly learn things or design new observables that pick up on things we didn't realize before. So I think this is a new way to visualize discrimination power that could potentially be exciting and useful. Okay, so now to be more specific about what's on this slide. Here's an example jet that we're trying to decide whether it's more likely to be a quark jet or a Z jet. At each node, I've plotted the log base 10 of the likelihood ratio from the two models. So a negative number means it's very quark-like, and a positive number means it's very Z-like. One of the main differences between quarks and Zs is the first splitting. So as I've said a couple times, a Z decays into QQ bar, and that's a pretty hard and symmetric in energy for splitting, whereas a quark just emits soft gluons. So this large negative number means that this first emission makes this really look like a quark jet that emitted a soft gluon and not a Z that decayed into QQ bar. And most of these numbers are negative, meaning that this jet is very quark-like. It also has a higher multiplicity. Here's a jet that's very Z-like. You can see by the color of the first two daughters that the energy is shared pretty symmetrically in the first splitting. So that looks a lot like a Z to QQ bar decay. It's also a low number of particles total in the jet, and the combination of these things makes this jet Z-like. Okay, so on to the next application, generating jets. Yeah?
Question. I didn't understand the probability of a jet. Could you explain what that means in the context of these examples?
Okay, so our model outputs a probability distribution, or our model takes in a jet and outputs a number that's between 0 and 1, and that if you summed over all the possible jets you could have shown the model, it would be normalized. So the output of our model is a probability distribution, and it's higher for jets that are realistic and lower for jets that are not realistic. And if you drew from that probability distribution, you would get a distribution of jets which are just like the ones that it was trained on, just like the training data distribution of jets. So that's the sense in which it's a probability. And in particular, it's a probability that you get after multiplying the probabilities assigned to each time step in the tree. Does that answer your question or part of it?
I mean, the probability is just the cross-section, right? So you have an event, right? And there's, in principle, you can calculate a differential cross-section, right? Calculate a distribution of that. But given a point in phase space, like given momenta, there exists some differential cross-section. It's impossible to calculate because it has, 20 particles or 100 particles or whatever it is. You can't calculate, and even if you could try, it's, very, very complicated, right? What you want to know is, given a set of particles, what is the differential cross-section if that set of particles came from a quark, or if that set of particles came from the decay of the Z boson. So you want those two differential cross-sections, d sigma d P1 through Pn for quark, and d sigma d Pn for Z. And the ratio of those is the relative probability, and he's calculating the log ratio. So that tells you whether it's more likely based on this cross-section. So the point phase space is consistent with both of them, and you just want to know how much more likely it is to be one or the other. And then he's breaking down that differential cross-section to each point in the clustering history. What is the contribution to that cross-section from each step? So he's writing as a probability of the cross-sections for each splitting, and then the full cross-section is the product of all of those steps. And then he's looking at each step to see which is the dominant step that tells you that it was more likely to be a Z or a quark.
But would you give any weighting for the parent side and the
Are you asking is there are three components that go into each number that I've written down, and which is the most important, like the splitting into the daughters or the parent that was chosen? Is that what you're asking?
Maybe. When you get to 6-39,
Yeah,
I'm assuming you're multiplying all these numbers.
that's right.
There's no weighting whatsoever.
That's right.
No, the weighting is the probability, right? You're defining the answer as the product of probabilities. So by definition, it's a product. Right?
Okay, but naively, maybe I'm totally off here, but on the left side, the first branch seems to have a sort of more weight to it.
So the first branch is a 10 to the minus 4 factor,
Yeah.
and this one is a 10 to the minus 0.4 factor, but we multiply all of them to get to 10 to the minus 39 or
I
whatever.
understand it, but you in this kind of sort of classification, you are thinking that the ones on the right-hand side will have an automatically lower sort of contribution. Is that-
No, you're not assuming that at all. That's not
Mhm.
Okay.
That's
So
the
you're
result.
saying that the branch at the end could be the deciding factor?
Yes, it could, yeah.
Okay, all right.
Yeah, and the branches at the end are the probabilities, assuming everything else has already happened. What's the probability of what's going to happen at that time step?
It makes perfect sense that the end doesn't matter, right? Because the difference, once the Z decays to quarks, then it's just quarks all around, right? And then they're just quarks. So the decay of a quark shouldn't depend on it. But of course, you're assuming this semi-classical idea of a Z decay, and there's really all the quantum mechanical interference. So that picture isn't quite accurate, but this model says that actually the discrimination power in the actual events, when you include these interference effects, actually is equivalent to the semi-classical picture. And that's why this 4.2 is the first step.
Okay, so for the next application, we can draw from our probability distribution, sample from it to generate example jets. So given a seed momentum, we can sample jets from our model, and we do this sequentially, time step by time step. At each time step, we decide whether or not the tree should end. If it does not end, which candidate particle should become the next splitter, and given a choice of the next parent, what should its daughter momenta be. Doing that, here's an example of a jet that we generated using our model, where now the number next to each node is the time step. So that's what happened first, second, third, fourth, fifth, sixth, seventh, and so on. Here's a few distributions showing that generation works pretty well. On the left, it's the mass distribution of the jets as compared between Pythia and our RNN generator. On the right, it's the multiplicity of the constituents in the jet compared between the two ways of generating jets. And on the bottom, it shows the correlations between these two observables, and you can see that we've gotten that right. On the left, it's the correlations between mass and multiplicity from Pythia. On the right, it's the correlation between mass and multiplicity using our RNN generator. So these look nice. Now I'll show you one that doesn't look quite as nice. But before I tell you why, let me just say that generating jets is a very rigorous test of all the model components, especially because we've written a sequential model. So very tiny errors at early time steps can propagate into big problems at later time steps. And that's really because our model is not optimized to generate jets. It's optimized to evaluate probabilities. Here's an example of an observable that, it learns pretty well, but definitely not perfectly. It's got some systematic errors. This is tau21 that I showed you earlier, which tells you something about whether there's one hard prong in the jet or two hard prongs in the jet. Okay, so the next application that I'll talk about avoids this problem of errors magnifying at later time steps. That's reweighting. So here I want to talk about reweighting simulated jets to agree with data distributions. So imagine that I could train two models. I can train a model on data jets, and I can train a model on simulated jets. And then I could take a sample of simulated jets and reweight the jets in that sample by the ratio of the two probabilities. And after doing that, the distributions generated by the simulator should match distributions generated in real data. Yeah.
Couldn't it be the case, though, that the fact that you have some mismatches is telling you about things that could have been better in the information there?
Are you going back to this picture, or are you asking about reweighting?
What I'm asking is whether, I understand what you're talking about reweighting,
Mm-hmm.
but rather than try to get rid of that difference,
Mhm.
can you learn from the difference?
Possibly. I haven't thought of a way to learn from it. As far as I understand it, the first splitting is just, it will never be perfect, no matter how long you train. And however amount of imperfectness that you have will amplify at later time steps. And I don't know if there's like some physics to be learned from that fact or not.
Did you try a different physics model for the branching? Maybe you did 2 to 3 branchings instead of 1 to 2 branchings?
You could definitely try different clustering algorithms, and we have tried a few. We've tried anti-KT. We haven't tried 2 to 3, but we've tried different 1 to 2 models.
Right, but I'm thinking 2 to 3 kind of has additional physics because you might put in more things like the covariance or something.
So 2 to 3 might make more sense from physics standpoint, yes. So one thing I want to say is that, like, mathematically, our model is capable of fitting any physics, including color coherence or anything that's described by 2 to 3 splittings. Our model mathematically should be able to describe it. Then the question is which one actually does better in practice with like finite training time and stuff. So it's possible that 2 to 3 could do better, but we haven't looked into it. Okay, so now let me just show you a proof of principle for this idea of reweighting. So we haven't trained on real data. We've just trained on 2 different sets of simulated data. To get 2 different sets of simulated data, I just varied the value of the strong coupling constant. In Pythia, the default value is 0.1365. I also varied it down to 0.11, and this changes distributions a bit. So here are the 2 tau21 distributions, and you can see there's a difference. And then here's what happens when we reweight the alpha s equals 0.11 distribution with the ratios of the probability. So it's not perfect, but this gives us some preliminary hope that this might be a useful application. Here's 2 other observables that we tried. There's tau32. Tau32 tells you something about whether or not there are 3 prongs or 2 prongs in the jet. You can see the two simulated sets of data have different distributions for tau32, but when we reweight, they're in much better agreement. There's also the cumulative energy fraction as a function of angle in the jet that disagrees in the 2 sets of data, but agrees much better after reweighting. And so you can see that this is definitely a promising application. Okay, so now let me summarize. So I've shown you our probabilistic model with a recurrent architecture that's been customized for jet evolution. I've said that it can be trained directly on data, though as a proof of principle, we've only trained it on simulated jets. It's got a transparent setup that lets us visualize what jet substructure the network has learned. And it's useful for jet discrimination, generation, and reweighting simulated jets to agree with data distributions. What we're hoping to do next is train on real LHC data. One problem with real LHC data is that there are no pure samples, but there are ways to get around that. And what's exciting is that we might, so quark-gluon jet discrimination has been a big problem for many years, and we're excited that we might be able to get a near optimal quark-gluon discriminator from our model and then be able to visualize what it learned that we haven't thought of before. We're also interested in reweighting jets from Monte Carlo simulations to agree with data once we've trained on data. And we're also thinking about perhaps expanding our model to describe full events rather than just isolated jets, maybe including quantum numbers, and maybe in other environments too. So I've talked about jets at an E plus E minus collider or at the LHC. Jets are much, much messier and much less well understood in heavy ion collisions, and maybe our model could be useful as a theoryless generator for jets and heavy ion collisions. Okay, that's all. Thanks.
Well, that was fantastic. Thank you.
Thanks.
Questions?
Yeah.
So when you
say you were using real data, I'm not really sure how with the simulation it works. First, you would feed it through this clustering algorithm.
Mm-hmm.
The jet radius, how is that chosen? Because would you hope that at some point you can just feed the data directly and somehow the machine could learn, like you wouldn't have to do this additional manual step of, clustering the momenta or whatever before feeding it into a neural net?
Are you concerned with the clustering into the tree or with the choice of jet radius that tells you how many particles you've clustered into the tree?
Right, like how trustworthy, like these clustering algorithms, like the choice, for example, of the maximum opening angle,
Mm-hmm.
which I think is the jet radius.
Yes.
You mentioned.
That's right.
How is that chosen, and how would that influence? Like, what if you choose it wrong?
I don't think there's any such thing as choosing it wrong. If you choose a big jet radius, you have a lot more information there. It's a lot messier too because you can catch emissions from more pile up or from other things that happen. If you have a narrow jet radius, then it's cleaner, but there's less information there, and so there are things to be gained from both large and small jet radii, and there's no wrong choice.
Other questions? Well, we asked a lot. I did actually want to make one comment, which is that it seems to me that this actually provides the basis of a really important thing that we here in astrophysics are doing. So when we detect, for us an event would be a rise in brightness and a fall in brightness, and with many millions of these being found every night, especially in the future with this new LSST project, one of the things that's really important is that as the event evolves, you'd like to compute the probability that it is one of any one of perhaps thousands of known types of variability. So it's a sequential evolving probability. The one difference is that you don't get it, you're able to see, because you have this nice algorithm, uniquely within the algorithm how the splits occur.
Mm-hmm.
We have times that are selected, and those may be selected having to do with a variety of reasons, like whether it was cloudy.
Mm-hmm.
But it really looks as if this is ideally suited for an important astrophysics problem, and it may be the basis for some collaboration. Okay, any other comments, questions?
How do you tackle overfitting?
So we actually didn't have a problem, but one thing that relates to overfitting is how many parameters we have in our model. So we chose the hidden dimensions to all be 100. I also tried 1,000, and we saw extreme overfitting in that case. But with 100, I guess maybe there just weren't enough parameters to overfit. There are lots of things you can do to handle overfitting, but we didn't have to do any of them.
Do you have training and test data?
Yes, we have that.
Cross-validation?
Yeah. So we see the training data, the loss decreasing, the test data, the loss decreasing right on top of each other the whole time, all the way to convergence.
Okay, there was another question.
If I understand that correctly, you feed the whole tree into your neural network.
Step by step.
Yeah. But you are determined by the physics of what is happening in one node. So wouldn't it be more efficient if you have a way smaller neural network you train with the inputs of a node and to generate an output probability for the 2 or 3 branches that are going on? And then just to chain those.
So perhaps it would be much more efficient, but you would also have to discard some physics because whatever happens at one node is sensitive to whatever else is in the jet at that time step. And so our model, all the inputs to what was happening in each node have as input this HT. So HT knows about the entire jet, and it's deciding what should happen at each node. So
Yeah, but if you look at the little blue
Yeah.
box at the bottom. So
Yes.
If I look at the top branch and the bottom branch,
mhm.
does the bottom branch really influence the top branch? I don't think so.
Well, all 4 branches in the picture are candidates for which particle could split next. So they are all sensitive to each other in determining the evolution of the tree.
The particles for the top two branches are to the left of it, right?
Excuse me, we should probably save this as a discussion because we have another group that is coming in to use the room. So I want to conclude, I want to thank all of the people from physics who came all the way over here. It's great to see that this is working out. Thank you, and thank you for a wonderful talk, Chris.
Yeah, so maybe I should say 3 instead of 4, but the 3 particles that are before the splitting, those are all candidates to be the next splitter, so the full global structure determines what happens at that time step.
Yeah, what I mean is, why don't you look at it particle by particle? If it's stable, okay, you are the end for that node, because it won't decay anymore. But if you are not stable, it can decay in 2 or 3 or maybe even 4 particles. So, and one of these decays forms a node, if I understand that correctly, the tree structure. So, the only thing that's interesting is what is happening in a node.
So we've organized our model sequentially so that at each time step only one particle splits. There's another way we could have done it where we could take each branch and separate them and analyze what happens in each branch subsequently separately. But then we.
That is a different.
It sounded to me that was related to what you were asking, where this one might have a chain of 4 decays, and then the one over here might have a chain of 3. But
yeah, but what I would I have no clue on particle physics. that first, but just by information, what I would try to do is set up a training for a neural network or maybe even a decision tree. What happens in one node? Because that seems to be very well determined. You know your inputs, and you have a kind of probability function for your outputs. Yeah,
reserved here at 11. Thank you.
Can I ask you a follow-up? Okay. So I guess when I asked the thing about the jet radius...
Is this yours, sir?
Yes.
Okay. When I don't fully understand about this algorithm, like let's say for example, I have a Higgs that decays into, I'm going to say it wrong because I...
Do you mind if I ask if you,
Yeah,
we're starting a meeting at 11. Thank you. I guess this one goes here. Okay. So I have some pretty cool slides, but I thought we'd keep the lights on so nobody falls asleep.
Do you want to, how do you want to do this?
I'd like to just
You want to get through it and then...
to go
talk,
through
or-
it,
Okay.
unless there's anything that you think is really like
No, I'll just try and write any notes or something.
okay. And so just the in addition to any comments that you're going to have, I guess what I'm looking for, one of the pieces of feedback I'm looking for specifically is I mean, my thing is I want to show how I'm, building the bridge or making the connection between local star formation and cosmology, and I want to know if that comes across effectively.
Sure. Okay.
Just a little bit over here. And one other caveat, I will probably be looking down a lot at my notes. I hope that will improve for the next week.
Sure. With practice, that'll be better, yeah.
Okay. All right. Well, let's see that this is this on. Okay, there we go. All right. Well, thank you for extending this kind invitation and for your hospitality. before I begin, I'd like to tell you about a couple of projects that I'm involved with at Harvard. Hi. I bet we're recording, huh? I'm going to wait till he is done. Okay. Before I begin,